This PowerPoint presentation covers the concept of buffer solutions from section 14.6 of our textbook. This first video will go over the basic definitions and concepts of buffer solutions and present some problem-solving strategies. Following videos will work through the calculations for specific examples. Before watching this video, make sure that you have completed the reading guides from section 14.6. Also, have a copy of the Chapter 14 handouts ready to take notes on as we work through this section. There are three important things that you need to know about a buffer solution. 1 is what it does, 2, what it's made of, and 3, how it works. A buffer is a solution that resists changes in pH when a small amount of either acid or base are added to it. Buffers are solutions that contain large concentrations of both a weak acid and its conjugate base. Buffers are able to resist changes in pH because their components can neutralize any added acid or base. Let's look at the beaker above with a generic buffer containing the weak acid HA and its conjugate base A-. If we add a small amount of strong acid to the buffer, the added acid will react with the base component of the buffer in a reaction that will go essentially to completion to neutralize the added H+. The H+ that's added reacts with the A-, the base in the buffer, to form HA. Since pH is defined as the negative log of the concentration of H+, and not the negative log of the concentration of HA, the pH of the buffer doesn't change very much when we add the acid because all of the added H+ gets neutralized. Similarly, adding a strong base like hydroxide to the buffer solution will not raise the pH very much because the added hydroxide is neutralized by the weak acid in the buffer. The neutralization reaction is hydroxide plus weak acid forms A- and water. Again, even though we're adding hydroxide ions, the concentration of hydroxide in solution isn't really increasing very much because the hydroxide ions are being neutralized by the acid component of the buffer. Whenever you're working with buffer solutions, there are several key problem-solving strategies to keep in mind. Since buffers contain weak acids and bases, we will need to use equilibrium concepts and Ka and Kb values to solve these problems. When given a buffer problem, make sure that you write down all the major species present first. Next, look for any reactions that go to completion. For example, because of the presence of a strong acid or base. You'll want to deal with these reactions using stoichiometry. Next, solve any relevant equilibria. Being careful to watch out for volume changes. If the volume is changing in the problem, you should probably do all the stoichiometry calculations in moles. There is also a very important equation that's used for calculating the pH values of buffer solutions. It's called the Henderson-Hasselbalch equation. This equation is derived from the Ka expression that we already know. If you take the Ka expression and take the negative log of both sides, you get negative log of Ka is equal to negative log of the ratio of the product of the concentrations of A- times H+ over the concentration of HA. Next, I'm going to use the rules of logs to separate the term on the right into two terms. Just like the negative log of the concentration of H+ is defined as pH, the negative log of the Ka value is defined as the pKa. pKa values for weak acids are shown in reference tables. So now we have that the pKa is going to be equal to the pH minus the log of the ratio of the concentration of the A- component to the concentration of the HA component. Finally, I'll rearrange this equation to solve for pH, and we have pH is equal to the pKa plus the log of the concentration of A- over the concentration of HA. This is the standard form for the Henderson-Hasselbalch equation. Notice that there really isn't anything new in this equation. It's just our old friend, the Ka expression, rearranged. Why is this equation so powerful for buffers? And if it's so great, why haven't we been using it all along? When you're dealing with a buffer solution, you typically know the concentrations of both weak acid and conjugate base components, the HA and A-. And so we can easily solve for the pH of the buffer using this equation. Why didn't we use this equation for determining the pH of a weak acid solution? Because if you're starting with just a solution of HA, for example, you won't know what to plug in for the concentration of A-. This is something that we had to find using an ice table. There is an assumption that's typically made when using the Henderson-Hasselbalch equation, and that is that the initial concentrations of the buffer components are not changed very much by their adjustment to reach equilibrium. This is the same as assuming that the x's are small in our ice table calculations. For most buffer calculation, this assumption is totally valid. In this presentation, we've looked at some basic concepts about buffer solutions and seen an important equation that can be used to solve for the pH of a buffer solution. Additional videos in this section will work through how to calculate the pH of a buffer solution before and after small amounts of acid or base are added to it.